11.2 Techniques for Evaluating Limits. In this section, we'll learn how to evaluate limits algebraically, mainly by two new techniques. Okay, let's take a look at an example here. It says find the limit as x approaches -3 of x squared plus x minus 6 all over x plus 3. So if you recall, one technique that we use, it's been a while now, is to use something called direct substitution. So what I do is I plug in everywhere I see x with -3. So if I plug in -3, right, we substitute directly, we end up with the following. That's going to be 9 minus 9 over 0. We get 0 over 0. So when you get the following, since we're dividing by 0, this is undefined. But not only is that when you have 0 over 0, this here is called the indeterminate form. Indeterminate form, meaning we cannot determine what the limit actually is. So if we get 0 over 0, this is called the indeterminate form. It just means we don't have enough information here. We actually don't know what the limit is. Well, direct substitution didn't work, but if we were to make a table, right, coming from the left-hand side, right, as you get closer and closer to -3 from the left side, we see that we approach -5, right? We get closer and closer to -5 in the y direction. As we look at the right-hand limit, right, we get closer and closer and closer to -3 from the right-hand side. We notice that our y value, right, also approaches -5. So because the left-hand limit and the right-hand limit are both approaching -5, we can see from the table that the limit will be -5. You could also see this from a graph. If I were to provide a graph for you, or if you were to sketch a graph, you'll notice that the limit as x approaches -3. So what you want to do is, like, you could look at, remember, it doesn't matter what happens at -3. We only care what happens as you come from the left-hand side and from the right-hand side. You'll notice that as you come from the left-hand side and you come from the right-hand side, they reach the same point, and that point is -5, right? So the limit as x approaches -3 for this function is equal to -5. What I'm trying to show is you can look at from a table and from the graph that the limit is -5. But we want to find a way to do this algebraically. When evaluating limits algebraically, the first thing you always want to try is direct substitution. But if you see that you are going to get 0 over 0, the indeterminate form, then that just means you'll have to do a little more work. Like, we have to simplify the function first and then directly substitute. So two main techniques we're looking at today is the dividing out techniques, where you just factor the numerator and denominator and cancel things out, and the rationalizing technique, where you multiply by the conjugate in the form of 1. So let's take a look at the dividing out technique. I'm going to go ahead and just take the function here. Okay, so again, this is like my scratch work. Remember, you do need to show proper limit notation to get full credit. X squared plus x minus 6 over x plus 3. If I plug in -3, remember from earlier, we got 0 over 0, indeterminate form, so I know that direct substitution doesn't work. But I can see that I can factor the numerator. So factor the numerator and simplify. So notice that the x plus 3's cancel out and I end up with x minus 2. So this entire function, this rational function, we were able to simplify as x minus 2. So I'm going to go ahead and rewrite that. I'm going to rewrite this as equaling the limit as x approaches -3 of x minus 2. And now I can directly substitute. So when you use up, right, when you use up that number, when you directly substitute, that's when you can drop that limit notation. So we get -3 minus 2, and our answer is -5. Again, I want to emphasize that you do need to use proper limit notation to get full credit. So you keep writing the limit of your function, and also there's no equal sign in between, up until you actually use up that number by direct substitution. If that confuses you, just always write that limit notation here, or in this case, the limit as x approaches -3, until you just get a single answer. Okay, so when you have the answer, you shouldn't write it as the limit of, right, because we're trying to find the limit. Okay, again, this would cost you points, putting an equal sign between the limit and the actual function, so don't do that. And then having your final answer as the following, right, that would also cost you points. Let's take a look at the graph of the function before we simplified and after we simplified, right? This was a function that we were originally given and we simplified it as follows. Notice that the only difference between the two functions is a whole at -3, and that's because we canceled out x plus 3 from both top and bottom, making x equals -3 a whole there, right? And so because the only difference between f of x and g of x is a whole, the limits stay the same for them at that location, right? Because remember, for limits, we don't care what actually happens there. We only care that the left-hand limit and the right-hand limit match, right? It doesn't matter what actually happens at that location. And that's why we can use this dividing out technique where you factor and simplify and then use direct substitution. Okay, let's take a look at a second example. It says find the limit. Again, the first thing you want to try is using direct substitution where we plug in the numbers. 1 cubed is 1, 1 squared is 1, and you end up with 0 over 0. It's the indeterminate form. That means we actually don't know what the limit is and we have to do more to it. So go ahead and try this problem. Find the limit using the dividing out technique. Okay, your final answer should be 1 over 2. So for this one, when you're simplifying the function part, in the denominator you have 4 terms. So you'll need to factor by grouping. Remember, you take the GCF of 2 terms at a time. You get a common factor of x minus 1, and then you're left with x squared plus 1. The x minus 1's cancel out. This is a simplified form, so we're going to take the same limit of the now simplified function, directly substitute. So if I plug it in directly, I end up with 1 over 2. Here's the graph of this function. Notice that the limit as x approaches 1 indeed is 1/2, right? It's indeed is 1/2 as you come the limit from the right hand side and the left hand side match, and that limit is 1/2. Let's take a look at another example. It says to find the limit. Now if I were to use direct substitution, I end up with a square root of 0 plus 1, which is just 1, minus 1 over 0. That gives me 0 over 0. Again, it's the indeterminate form. Indeterminate form. So that just tells me I need to simplify first and then try direct substitution. The second technique we're looking at is the rationalizing technique. And normally we rationalize denominators, right? We want to get rid of radicals from the denominator, so we rationalize, or imaginary numbers from the denominator. But when using this technique to evaluate limits, you want to rationalize the numerator of the function. And the technique is the same. You want to multiply by the conjugate in the form of 1. So let's just recall the following. If you are given a plus b, what is the conjugate going to be? Okay, the conjugate is going to be a minus b. What if you're given the square root of x plus 4? What is the conjugate of that? It's going to be square root of x minus 4. What if you're given the square root of x plus 1 minus 1? What's the conjugate of this one? It's going to be the square root of x plus 1 plus 1. Let's do one more. What if I am given 2 minus the square root of x plus 9? What is the conjugate of this? It's 2 plus the square root of x plus 9. Remember, it's just the middle term that's going to change from plus to minus, or minus to plus. Everything else to the thing from to the left of it and the term on the right of it stays the same. So that's just a recap on what the conjugate is. Okay, so let's take a look at this example, finding the limit. Again, we already tried direct substitution and it didn't work because we ended up with an indeterminate form. So I'm going to have to rationalize this, right? Again, I have that radical in the numerator right now and I want to get rid of it, and it's going to end up being in the denominator. So what I do is I multiply by the form of 1 by the conjugate. So what is the conjugate of the numerator here? It's going to be square root of x plus 1 plus 1. And I need to do that in the form of 1 so I'm not changing the value of the overall expression. So let's go ahead and do the following. I'm going to go ahead and multiply straight across. And if you remember, when we multiply conjugates, the beauty of this is that the middle terms are going to cancel out. You're going to end up with a difference of squares. So if I FOIL this out, I end up with x plus 1, because the square roots cancel out. I get a plus square root of x plus 1 minus the square root of x plus 1. Again, those cancel out. I end up with just minus 1. Again, when you multiply conjugate conjugate, the middle terms are going to cancel out. And then the denominator, I'm going to just keep it as is. It's x times the square root of x plus 1 plus 1. Okay, so if I simplify this out, notice that the 1's cancel out here. Minus 1 is 0, so it's just x. I get x over x times this entire quantity. And now I can cancel out these x's, ending up with 1 over square root of x plus 1 plus 1. So I've simplified this out, right? Notice that canceling out the x's right here was key because we're plugging in 0 and we don't want to get 0 over 0. So that's the part that we wanted to see happen. So now that I've rationalized the function, again, I've rationalized the numerator. Now notice that the radical is now in the denominator now, not in the numerator. I can go ahead and take the simplified form and use direct substitution. So this is equal to the limit as x approaches 0 of the simplified form of 1 over square root of x plus 1 plus 1. Okay, it's simplified for this purpose of finding the limit. Now I can use direct substitution. If I use direct substitution, I get 0 plus 1, which is 1. That gives me 1 over 2, and that is your final answer. Here's a graph of this function. Notice that the limit as x approaches 0, right? The left-hand limit and the right-hand limit are both the same, and it is indeed 1 over 2. Taking a look at a table of this function, right? As you approach 0 from the left-hand side, right, you're getting closer and closer to 0 coming from the left side of the number line. You get closer and closer to 0.5. As you approach 0 from the right-hand side, right, 0.1 and then 0.01, 0.001, you're getting closer to 0. Notice that the overall value, or the y value of the function, is also getting closer and closer to 0.5. And remember, the limit here, we know, is equal to 0.5. But your job for this section is to be able to do this using the algebraic technique. You try, find the limit. Okay, so if you use direct substitution, you'll see that you get 0 over 0, the indeterminate form. That means you need to simplify the function first. So we can simplify this function. I see a radical, so I can use a rationalizing technique by multiplying by the form of 1 in the form of the conjugate, right? So instead of minus, I have a plus. And then when I FOIL this out, right, square root of times square gives you just the x plus 9, just the radicand. I get plus 3 times the root, minus 3 times the root, and negative 3 times 3 gives me minus 9. Again, the middle terms cancel out. You don't have to show that part. I just want to show it in case some of you want to see it written out. Then you'll notice that the 9 minus 9 also cancels out, so you end up with x over x times this quantity. The x's also cancel out, so you end up with 1 over this entire chunk here. So from here, we can now use direct substitution. So I'm going to go ahead and rewrite the limit first. The limit as x approaches 0 of 1 over the square root of x plus 9 plus 3. And now I can plug in the number here, the 0 here. So square root of 9 plus 3, that's just going to be 1 over 3 plus 3, give me 6. 1 over 6 is your final answer. Again, to recap, to evaluate limits algebraically, always try direct substitution first. And if it doesn't work, you get an indeterminate form of 0 over 0, you will need to simplify and then direct substitute. So 2 of the simplification process that we looked at was the dividing out technique and the rationalizing technique. You may also need to just simplify. You might have complex fractions where you need to make it into a single fraction over a single fraction, and then multiply by the reciprocal, and then do direct substitution. You'll see like 1 or 2 problems in the homework like that.